Alright, welcome to The Explainer. Today we are cracking a 2,000-year-old code, a mystery about a building material so ridiculously advanced, it seems to just laugh at time itself. Yeah, we're talking about Roman concrete. So let's just jump right in with something that should blow your mind. On one side, you have the Roman Via Appia. It was built in 312 BCE and you can still walk on parts of it today. On the other side, the asphalt highway you drive on every day, which is lucky if it lasts 20 years before it's a cracked, pothole-ridden mess. This isn't just a slight improvement. This is a paradox that points to a lost form of genius. So how on earth did they do it? I mean, this is the central question, right? How did they create a material that actually gets stronger with age, while our modern, high-tech stuff starts falling apart almost immediately? Well, that's the mystery we're going to solve today, and the answer could literally change the way we build our world. You see, a Roman road was never just a road. It was a deeply engineered system. They built it from the ground up in 4 distinct layers. They started with the stodamen, the solid footing of large flat stones. Then came the rudis, smaller stones packed in with mortar. On top of that, the nucleus, a solid concrete base. And finally, the iconic summum dorsum, those perfectly fitted paving stones. Each layer had a job, working together like a team to handle centuries of traffic. But their genius didn't stop with the layers. Oh no, they understood the physics of their biggest enemy, water. See that slight curve? That's called a camber. It looks simple, but it's an absolutely brilliant piece of engineering. It ensures that rainwater runs off immediately instead of soaking in and destroying the road from the inside out. They knew 2,000 years ago that to last forever, you first had to defeat water. I mean, just let that sink in. The sheer scale of this it's staggering. It's not just a little better. It's lasted for over 100 generations. So this forces the question, what was their secret? What did they know that we've somehow forgotten? Well, the answer, believe it or not, starts deep inside a volcano. So that brings us to the secret ingredient. And to find it, we have to go deep into the fiery heart of Italy, to a place called the Campi Flegrei caldera. This isn't just any volcano. It's a massive collapsed supervolcano that has coated the entire region with a very special kind of volcanic ash, an ash the Romans called the dust of Puteoli. This stuff, which we now call Pozzolana, wasn't just any old ash. It was a geological jackpot. Its real power lies in its chemical structure, or maybe, more accurately, its total lack of structure. Okay. This is where it gets really cool, down at the atomic level. Think about normal sand, right? That's crystalline silica. Its atoms are all neat and tidy, locked into a stable, orderly grid. They're happy, stable, lazy. But the silica in this volcanic ash is amorphous. The insane heat and rapid cooling of the eruption froze its atoms into a chaotic, disordered, high-energy state. It is chemically frustrated. It is desperate to react and find stability. And that reactivity is the engine behind this entire miracle. And right here, this is the magic written in the language of chemistry. You take calcium hydroxide, which is just slaked lime, and you mix it with that reactive amorphous silica from the Pozzolana. What you get is a slow, powerful reaction that creates a brand new compound we call CSH. Now this stuff, CSH, calcium silicate hydrate, it's the molecular glue in our modern concrete too, but, and this is a huge but, the Roman version is completely different. Because it formed so slowly from that pozzolanic reaction, it created a unique molecular structure, with incredibly long, interlocking crystals that are far more resistant to fracture. The Romans weren't just making artificial rock, in a way, they were growing it. Okay, so volcanic ash was one half of this incredible recipe. The other half? Well, that started with fire. The Romans would take ordinary limestone, calcium carbonate, or CaCO3, and they'd cook it in kilns at about 900 degrees Celsius. This process, called calcination, burns off the carbon dioxide, the CO2, and what's left behind is this highly unstable, super reactive powder called calcium oxide, or quicklime. Now, for the longest time, the thinking was that they'd then slake this quicklime by adding water, which creates this intense, boiling hot reaction that produces calcium hydroxide or slaked lime. But a recent, absolutely revolutionary breakthrough suggests they did something way, way more daring. And here it is. This is the game changer, the hot mixing hypothesis. The evidence is mounting that they didn't pre-slick the lime at all. They threw the hyper-reactive quicklime directly into the wet concrete mix. This would have created thousands of tiny pockets of intense heat inside the concrete as it cured, forging unique chemical bonds and leaving behind some very specific evidence. You know, for centuries, scientists looked at these little white chunks in Roman concrete and just thought, sloppy mixing. Turns out they were looking at the secret to its immortality. These aren't mistakes, they're lime clasts, and you can think of each one as a tiny chemical savings account, a reservoir of pure calcium just waiting to be activated. So check this out. Here's how this brilliant self-healing actually works. It's almost alive. First, a tiny microcrack forms, water gets in, but instead of causing damage, that water finds one of these dormant lime clasts. The water reacts with the clast, dissolving the calcium and creating a supersaturated solution that flows right into the crack. Then it recrystallizes as calcium carbonate, literally stitching the crack shut from the inside out. This concrete doesn't just resist damage, it actively heals itself. Alright, so you have a self-healing material. What's next? You take it and you throw it into the most hostile environment on the planet, the open ocean. At Caesarea Maritima, they built a massive harbor by pouring their concrete into wooden forms and sinking them directly into the sea. For modern materials, this would be a complete disaster. For any modern engineer, this is insane. Salt water is a cancer for modern concrete. The chlorides and sulfates in it cause a chemical reaction that literally tears the material apart from the inside. But for Roman concrete, the exact opposite happens. Seawater isn't the enemy. It's the final ingredient, the key that unlocks its ultimate form. So what's going on? Well, the first of these miracle minerals is called Tobermorite. Now this stuff is incredibly rare. It almost never forms in modern concrete because it requires very specific conditions. But in the Roman recipe, seawater percolating through that Pozzolana mix slowly grows these beautiful plate-like crystals over hundreds of years, interlocking and reinforcing the entire structure. And it doesn't stop there. The second mineral is called Phillipsite. This is a type of zeolite, and it grows inside the tiny pores of the concrete, forming a complex 3D framework. It acts like a microscopic cage, trapping all the harmful salt ions that would have destroyed modern concrete. Together, these two minerals are literally like a coral reef growing inside the structure, building a crystal armor over millennia. So let's just break this down. You have Tobermorite providing fracture toughness. Its molecules are actually flexible, allowing the concrete to bend instead of shattering. And then you have Phillipsite, which grabs and traps those destructive salt ions. It literally turns the ocean's attack into a source of ever-increasing strength. Okay, so we've cracked the chemical code. Now, what happens when you give this miraculous material to some of the greatest engineering minds in history? You get buildings that defy time itself, and there is no better example than the Pantheon. I mean, just think about this. Even today, the Pantheon's dome is still the largest unreinforced concrete dome on the entire planet. It spans a massive 43.3 meters. To hold up all that weight, the concrete at the base of the dome is a colossal 6 meters thick, engineered for pure, unadulterated compressive strength. But as you get to the top, near that famous opening to the sky, the oculus, the dome, thins out to just 1.2 meters. This wasn't just building. This was a level of structural optimization that is still breathtaking today. And this is the part that just shows their absolute genius. They didn't use one kind of concrete. They engineered custom recipes for each part of the dome. At the bottom, they used heavy basalt rock as their aggregate. In the middle section, a lighter volcanic rock called tufa, and at the very top, around the crown, they mixed in pumice, a volcanic rock so light it actually floats on water. They made the building lighter the higher they went. It's a masterclass, and it wasn't a one-off trick. They applied this exact same principle of graduated concrete density to build the Colosseum. The foundations used heavy aggregates, while the upper vaults used lightweight ones. The building wasn't just a stadium, it was a precision-engineered machine for spectacle, and the concrete was tuned perfectly for every single part of it. So, it's incredible. We've unearthed this lost technology. But that brings us to the biggest and maybe the most important question of all. What do we do with this knowledge now, today, as we face our own global infrastructure crisis? Well, for one, the environmental case is absolutely staggering. I mean, look at this. Modern cement production is responsible for about 8% of global CO2 emissions. A Roman-style binder, because it's cooked at much lower temperatures, can produce up to 75% less CO2. And that's before you even consider that it lasts hundreds, if not thousands of years longer. And please don't think this is just some cool history lesson. This is happening right now. Technologies like LC3 or limestone calcine clay cement are a direct modern descendant of the Roman recipe. They use abundant clays, cook them to make them reactive, and use them as a pozzolana to create a super strong, low-carbon alternative to modern cement. You know, this ancient wisdom is already being put to work on cutting-edge projects all over the world. In Singapore, they're using pozzolanic blends for massive underwater port structures. There are projects designing seawalls that are meant to grow those Phillipsite crystals when seawater hits them. And in Europe, they're developing highway barriers with that hot mixed lime class technology to make them self-healing. The Roman engineering renaissance is here. But you know, at its core, this is about more than just chemistry. It's about a total shift in philosophy. The Romans built for eternity, not for the next financial quarter. They made a massive upfront investment in durability, and that investment is still paying off 2,000 years later. If we could just recapture a fraction of that long-term thinking, the impact would be transformative. You know, in the end, time is the ultimate stress test. It's the final judge of everything we create. Roman concrete? It passed. It passed with flying colors. And now, as we face our own monumental challenges of a changing climate and crumbling infrastructure, the test is ours.